All right, let's dive right in. Today, we're unlocking the secrets of what might be the single most important element for life as we know it. We're talking about the one that builds our entire world, molecule by molecule. We're investigating the secrets of carbon.
So let me ask you a question. It sounds kind of like a riddle, right? What could possibly connect a brilliant, hard-as-nails gemstone, the food that you eat, and the literal blueprint of your existence? They seem like they're from completely different worlds.
Well, the answer is carbon. But, that simple answer just opens up a much, much deeper mystery. Because for an element that is so completely fundamental, that forms the backbone of millions of compounds, there's a really surprising twist.
And here's the paradox. You'd think it would be one of the most common elements out there, right? But it's not. Carbon makes up this absolutely tiny fraction of our planet's crust and atmosphere. We're talking just 0.02% and 0.03%. For how important it is, it's shockingly rare. And that brings us to the central question for today. How in the world does this relatively uncommon element become the master architect of, well, pretty much everything? To solve this mystery, we've got to look for clues, and we've got to start at the atomic level.
So our first clue, it's all about how carbon atoms interact with other atoms. See, it's not about taking or giving. For carbon, the secret is all about sharing.
Okay, so every atom's goal is to have a full, stable outer shell of electrons. Carbon has 4 of them, which puts it in a really tough spot. I mean, trying to gain 4 more would create this super unstable negative charge. But losing all 4? That would take a colossal amount of energy. So it does neither. Carbon finds a much more elegant solution. Carbon shares its electrons. It forms something called a covalent bond. And you can just think of it like a firm, cooperative handshake between atoms. By sharing its 4 electrons with other atoms, it gets that perfect, stable state it's looking for, all without the drama of gaining or losing anything. This sharing is the absolute fundamental secret to its stability.
Now, sharing is one thing, but to build the universe of molecules that it does, carbon needs something more. And this brings us to our second clue. Carbon has 2 unique superpowers that basically no other element can match.
Its first superpower is called catenation. And all that means is that carbon has this incredible ability to form strong, stable bonds with itself over and over again. This lets it create these long chains and complex rings. The carbon-carbon bond is just exceptionally strong, allowing it to build these huge, intricate molecular skeletons.
The second superpower is called tetravalency. Tetra just means 4. Because it has those 4 outer electrons to share, each carbon atom can form 4 separate bonds. The best way to think about it is like a universal Lego brick. It's got 4 connection points, which lets it build outwards in 3 dimensions with incredible versatility. And when you combine these 2 superpowers, the ability to link to itself and the ability to form 4 bonds, something truly amazing happens. You can take a chunk of pure carbon and, just by arranging the atoms differently, create materials that seem like they're from different planets.
Just look at diamond and graphite. In a diamond, every single carbon atom is bonded to 4 others in this super rigid 3D lattice. That's what makes it the hardest natural substance we know. But in graphite, each carbon bonds to only 3 others, forming these flat sheets that just slide right over each other. This makes it soft and slippery. It's literally the lead in your pencil. Same element, totally different worlds. It's just incredible.
So, when you put all these clues together, the sharing, the self-linking, the 4 connection points, the result is just staggering. It's the launch pad for a nearly infinite number of compounds, especially when carbon starts bonding with other elements.
Let's start with the basics. The most fundamental family of carbon compounds are the hydrocarbons. That's it, just carbon and hydrogen. But even within this really simple family, the variety is immense. These form the basis for fuels we use every day, like methane and propane.
Now, we can split these hydrocarbons into 2 main types. You've got your saturated ones, which only have single carbon-carbon bonds. They're pretty stable, kind of chill, and less reactive. But then you have unsaturated ones, which have double or even triple bonds. And these bonds are like coiled springs, just ready to snap open and react, which makes them way more chemically active.
But the real magic, the real fun, happens when we start swapping out some of those hydrogen atoms for other elements, things like oxygen or nitrogen. These new attachments are called functional groups, and each one gives the carbon backbone a whole new chemical personality. You add an OH group, and boom, it's an alcohol. Add a COOH group, and now it's an acid. This is how we get from simple fuels to things like complex medicines.
Okay, so we've dug into the atomic secrets. Now, let's see how these clues actually solve a real-world mystery that you've probably faced, cleaning up a greasy mess.
Come on, we've all been there. You've got oil or grease, and you know that oil and water just do not mix. So how does soap, which is a classic carbon compound, magically bridge that gap and wash all that grease away?
Well, the secret is all in the soap molecule's brilliant design. It has two different ends. It's got a long hydrocarbon tail that's hydrophobic, meaning it hates water but loves oil, and it's got an ionic head that's hydrophilic, meaning it loves water. This two-faced nature is its secret weapon.
So here's exactly what happens. When you add soap to greasy water, all those oil-loving tails dive right into the grease droplet. Meanwhile, the water-loving heads stay on the outside facing the water. They form this tiny little sphere called a micelle, which completely traps the grease inside. And just like that, the grease is hidden in a nice, water-soluble package that can be rinsed away. It's so clever.
And here's a final practical point. This is exactly why we have detergents today. You see, traditional soap doesn't work so well in hard water because it reacts with the minerals and forms that nasty soap scum. Modern detergents are also carbon-based, but they're designed so their water-loving heads don't form scum. That means they work great no matter what kind of water you have.
So there you have it. We've cracked the case. The secret to carbon's incredible power really comes down to three things: its elegant solution of sharing electrons in covalent bonds, and its two amazing superpowers: catenation, that ability to chain to itself, and tetravalency, its super versatile four-way bonding.
You know, for a long time, scientists actually believed these amazing molecules could only be made by some kind of vital force that was only found inside living things. But back in 1828, a guy named Friedrich Wöhler actually made an organic compound in his lab. He proved that the chemistry of life was, well, just chemistry, and we still call it organic chemistry to this day.
So that leaves us with one final thought. We've seen how this single, humble element can build everything from a simple soap molecule to the incredibly complex code of life itself. And it really makes you wonder, what are the limits? What else can carbon create? That's definitely something to think about.